All right, ladies and gentlemen, in this video, we are continuing our discussion on area of regular polygons. In our previous video, we went ahead and just identified some key terminologies like apothem and central angle and radius and the center of the circle. We found out how to find the central angle. And now we're going to go ahead and look at specifically finding the area of any regular n-gon and a concept by dividing it into congruent triangles. So let's think about this. If we have a polygon, and if you continued this to however you went, every time that you drew a radius, we talked about this in our previous video, you create a specific congruent pair or set of triangles, depending on the number of sides you will have. And so if you can find the area of one of those triangles, you really end up finding all of your specific area you're finding, depending on whatever it may be. So the area of a regular polygon is the area of one of the triangles created times the number of triangles that you actually have. All right, well, if we think about that, the area of one triangle, right, is half the base times the height, right? Well, our base is whatever the side length is. I don't know what the side length is, but whatever that side length actually is the base of a triangle. A for apothem, remember apothem was just the height of one of those triangles. So it's half times the base, the side length, times A, our apothem, which was just the height, times the number of triangles that we actually have. So if we use our commutative and associative properties of multiplication, that's the same thing as saying it's half of the height times the number of sides times the side length. Well, why did I want to break this up? Because the number of sides in the polygon, however there may be, times the value of each of those side lengths is really just the perimeter of the entire polygon, right? That's really all that it is. And the reason why we kind of break it down, I know some of you guys are like, well, why are we making it more complicated? If it's just this top formula, why can't we leave it as that top formula? Well, you can, but I want to also show how it can be kind of further dove into to see how it's a relationship between the number of sides and the side lengths, making it a correspondence to the perimeter. Because now we can use it as possibly a way to find the perimeter if we don't know a side length. So, as you kind of see here, here is a summation of our last slide. So it says the area is equal to half the apothem times the perimeter, or if you want to think of it this way, it's half of the apothem times the number of sides times the value of the side length, right, which is kind of our base of the triangles. So let's take a look here at an example of how we can kind of utilize this. So, I'm sorry. There it is. All right. So if we want to go ahead and find the area of our regular polygon here, we're going to go ahead and find the area of this regular hexagon that I have, okay? So what I did here is I blew up the triangle. This is not a separate problem. All I did was I took our triangle right in here and I just blew it up, all right? I just blew it up a little bit. And let's break this problem down a little before we go any farther. All right, so remember, these two radii are congruent. So these are congruent to one another. They're congruent to one another here. I need to know what the value of the apothem is. Remember, our area formula is equal to half of the apothem times the perimeter, or half of the apothem times the number of sides times the side lengths. We have a hexagon, so we have 6 sides that we know. We know the whole side length is 3. So I'm going to kind of start this off by saying that I know for sure that it's half of A times the number of sides, 6, times the side length of 3. Okay, but I still don't know A. But look at what happens end up here. look at what we know about this particular hexagon or triangle that we're talking about, okay? Well, what did we create? Let's think about this. What did we create here specifically? Well, we know that the apothem makes a perpendicular. If this angle right here, if our whole triangle is considered equilateral, then this apothem becomes an angle bisector, and we end up getting a 30-degree angle right in here. So we get a 30-degree angle. If this is 90, this angle is going to be 60 degrees, right? It's going to be 60 degrees. Well, ladies and gentlemen, that becomes a 30, 60, 90 right triangle. This is not new for us. We've talked about 30, 60, 90 right triangles. Or you can think of it in terms of trig functions. I have this angle, the adjacent apothem is what we want to find. I know the opposite of 1.5, so I could use tangent as well too. There's a lot of different varieties and ways that we can kind of go about this particular problem here. So let's think about this. If this is the case, what do we know? Let's go ahead and use our trig functions. All right, I love using trig functions more than anything. So let's use trig functions. Try to find this out. The tangent of 30 degrees will be equal to its opposite 1.5 over the adjacent, which is my apothem. I don't know what it is. We get to find it. And so we end up seeing that we get x times the tangent of 30 equals 1.5. So x will equal 1.5 divided by the tangent of 30. All right, so let's take a look here, and let's keep in mind that for most people that are taking this course, we're not in pre-calculus yet, so tangent of 30 is something that we're going to definitely know kind of off the top of our head, but let's just do this without really realizing our unit circle and all that stuff as well too. So 1.5 divided by the tangent of 30 is going to end up getting us about 2.6. All right, we'll call about 2.6 right there. So we'll use 2.6 as our value for our apothem. So equals 2.6 for the value of the apothem. So let me break this down here. So now we have that the area is going to equal 1/2 of our apothem, 2.6, times 6 and times 3, right? Going back to our number of sides and our side length. Area equals 1/2 of 2.6 times 6 times 3. Well, 6 times 3 is 18. Divided by 2 is 9. So really it's 9 times 2.6, which is about 23.4 meters squared. And that is the area of this entire hexagon. Now let's kind of recap just real quick. Now, of course, if you understand it, you can kind of close the video up, but let's just recap. First and foremost, what did we do? We identified the pieces of the formula that we knew. We knew that there was number of sides being 6 because it's a hexagon. We knew the side length was 3 meters because it told us, right? We had to find the apothem. So how did we find the apothem? Well, we blew up this triangle right here to realize that since this is a hexagon, the central angle ends up being 60 degrees, right? 360 divided by 6 for the number of central angles that would be. There would be 60 degrees. Well, the apothem would angle bisect an equilateral triangle. And so that means that degree measure was 30 degrees. If this is 30 degrees, that means this one is to be 60 degrees of my right triangle that is created. So I took the tangent of 30 degrees is opposite over adjacent and found the length of my apothem. And I went ahead and used that 1.5 divided by tangent of 30 to find 2.6. Then I substitute it right back on in to get 23.4.